one. Let's see. Is there a way for me to just quickly share the stream? It would be cool to automatically share it in Twitter, but I don't think I can do that from Twitch Studio. Although I can easily just go to twitch.com and certain sys. I think this is right. Is this the correct thing? No. Systems. I don't even know my URL. There you go. So twitter.com. Let's go. Let's go. So Fourier transforms and SymPy. So what are we doing? So this is basically the stuff that is required for this exercise here. And again, I'm just tired of fighting with this one. So I'm going to be, it's just because it does not, something does not work as I expect it to work. And I think I've done smaller examples and it seems to work well. So if I just say Python x2_1 and let it run. I forgot which is the one. My guess is is somewhere to do with the sort of the range of the integral, you know, because these is like, I don't even know where they take that, where they take that from. Where's pi popping up here? Like even if you would say you do infinite, even if you do infinite, oh well, great, that doesn't work. But if you just let it indefinite, which I don't think is what we have to do, because again, let's remember the shape this has, right? It's like a decay thing like this. It's even like, the thing is that, you know, even R is not something you can get rid of. Like how do I get rid of R? How is that only dependent on alpha? There's got to be some step that I'm missing, or some kind of constraint that I'm missing, because again, the actual integral is being done by SymPy, right? But all I'm doing is, I know this is real, I know that R is real and positive. We know n can be complex, so we don't really know much anything about n. And then I think that is the correct way of expressing these. It's n times e to the power of minus alpha times r. We conjugate that, and so we print these here, and then basically we do the integral with respect to r. Maybe that's kind of the thing. Maybe there's something else in here, but the integral with respect to r, and we integrate that, and that always gives us something that still depends on r. Because the exponential is its own integral at the end of the day, right? So this all makes sense. And then I solve these for n, right? So again, remember, that's what we want. We want to make sure that the integral is the area under the integral, sorry, whatever I'm saying, the area under the probability density function. So the integral that we just calculated equals to 1, and we solve for n. And I get that thing here. For a equal, not equal to 0. this is square root of 2. So, I mean, you know, there's potential here. Maybe this is actually not that different from that, right? This is simplified. Let me see if I can get Sir Edge. Hi, Sir Edge. I'm basically following this stuff in here from this document. This is all, by the way, if you go to uncertain.system/roadmap, I linked the actual file in here, and it's basically this PDF. And so what I'm doing is I'm doing problem 2.1, but I'm trying to basically do it in a way that, so I try to actually learn SymPy at the same time and try to solve this with SymPy instead of just kind of doing all the stuff manually, which I know it's a bit lazy, but at the end of the day, it's kind of, I think it's sort of, it's a more convenient tool, and I'm learning a lot of other stuff at the same time, so it's good. And then, you know, it is important. One of the things that I want to do with these is I truly understand, you know, why certain mathematical concepts are being used, right? So it's not like that's a solution, that's what the solution should look like, and let's go for it. But it's more like, you know, I actually spent some time a month ago, because I did took a bit of a break for another project, but, you know, looking at things like the momentum conversion from space, so from position space. And I'm trying to understand why a Fourier transform is what it's used, right? So kind of really trying to go down sort of the first principles of why these specific mathematical constructs are used for certain things, but then not really diving too much into the, hey, let's do this integral by hand. So using modern tools for this. But again, I'm stuck since like 5 streams or something on just the first part here, which is compute the normalization factor of n, which should be fairly straightforward, because it's you calculate the probability density, and that's what normalization means, right? So you want wave functions that give you a normalized probability density function. So this means that these probabilities are kind of adding up to 1 in a way, and so you do that by integrating the product of these and its conjugate, and yeah, and then kind of solving for n when the whole expression equals 1. And the problem I'm having is this gives me this thing here, which is not exactly, let's see if I can open Paint and try to maybe do something by hand a little bit, because I don't know how to do this in, how can I manipulate expressions easily in SymPy like this. Maybe I should learn that, but so, I mean, square root of 2 is nothing else than 2 to the power of like a half, and then times, and then we have minus a to the power of a half, and then we have e to the power of a times r. A is alpha, no, but that has nothing to do with this, because here we have alpha. So first of all, alpha, not minus alpha, to the, yeah, it just makes no sense. If I do smaller, if I do kind of, that is the way to solve these kind of questions, but for some reason that's, my guess is I'm doing the, I instead of doing an indefinite integral, I could probably do a finite integral, because I know that, for example, for r, for values below 0 make no sense anyway. But then I don't really know where would be the other limit, right? Even if I just put something like random, that still does not give me any good answer, I think. So n should be independent of r, right? Since you should integrate over r from 0 to infinite. Do I have to integrate from 0 to infinite? Probably. But I do 0 to infinite, because that's what will make sense, because it's kind of has like a decay shape, right? I mean, it seems to me, the thing is, this breaks. I don't know why it breaks. Maybe because, maybe because I have sort of a kind of partial I don't know why this breaks. So invalid NaN comparison. I'll have to look into these, I guess. This is the range that makes the most sense, and I think, I mean, it's got to be definitely independent from R because it's the the normalization coefficient, right? So it's, in a way, it's just a weight. So I don't know. I just, to be honest, I just kind of have today. I wanted to kind of do I'm doing short session, so I wanted to spend some more time on digging into the how to do the transformation to the momentum representation in SymPy. At least try to start attacking that, because I have no idea how to do that in SymPy. And so what I'm gonna do is SymPy, and then so position to momentum conversion, Python. Let's just leave that bit out. I know it's an integral, what I have to do, but I don't even know where to start. So suppose we have a three-dimensional wave function in position space. That's what we have. We can write these functions as a weighted sum of orthogonal basis functions, or in the continuous case as an integral case space. I'm not sure I understand this notation though. It is clear that if we specify the set of functions psi sub k, say as a set of eigenfunctions of the momentum operator, the function holds all the information necessary to reconstruct psi r and is therefore an alternative description of the state psi. So is it all what you're doing? In quantum mechanics, the momentum operator is given by these. So I definitely want to understand that. Eigenfunctions. Position operator. So it's an integral. But that's too abstract to digest for me at the moment. Let's try to understand that. So there's a momentum operator. I don't know what this K space is in here. So transform from position to momentum space. Mathematically, the duality between position and momentum is an example of Pontryagin duality. I think I read that. So the Fourier transform obtains the function in momentum space. So I just have to do the Fourier transform, which is just this stuff. Okay, so this is position, this is momentum. We can Fourier transform from one to another. We have the symmetric Fourier transform. Okay, so this is probably just the textbook, hey, that's how you do it, right? So you have your wave function. What is px, ipx? It's an integral. Okay, so this is what you have to do. These formulas are worth a little study if we define it, we say with definite momentum. Okay, this is definitely worth a read. But it seems to be what has to be done. So this is a K to P. So you're multiplying the function by these. It's an integral, so you're multiplying. I forgot why this multiplication made sense. It's because each of these components, I'm trying to think about not the real case, but sort of the sum case instead of an integral, right? Each of these components is like you're trying to approximate. This is like Fourier serious thing. Right, in a way. Oh yeah, I remember. This is because, so this is just notation, right? Because because this translates to like a sine plus cosine, like one of those components is complex, and so it's just a way to say you like how kind of much weight like a pure sinus wave has into this, and so kind of you're using these to build up then the momentum representation. Yeah. Man, I did that a month ago and I forgot already. Fourier. Yeah. Exactly. Because this is what you want to do. You want to kind of have those cosine things, and so yeah, that's why having it with the exponential notation makes sense, because then I think the complex parts cancel out. Yeah, something like this. But again, what I'm trying to do is write these thing here and sort of in the momentum version, because what I want to do is that I want to show that the probability density of finding the particle with momentum h bar k is isotropic, aka does not depend on the position but just the radius, then maybe. And I want to see, I'm gonna sneak peek into at least the first step of the solution, because I want to see what are they doing here, which is funny because I already see that I don't see what I would have expected. I guess I do see this kind of stuff here, which is I guess the same notation that you have here, just k is replaced by P in here. I don't see that part, which worries me a bit. And then this is, and I also don't see, oh yeah, no, it's kind of, it's cool because it's e to the power of minus, so this is the actual wave function here. But then it's times the same thing, so it's just added. Oh, I do see the 2 pi in here. Why? Why is that? And so then it's just like they're going is like, oh, that's proportional. Okay, and so the rest I don't want to look like, but let's. Yeah, I should just try to do the B and then just do it. But again, I just talked too much today and too less doing. Just don't have all the time I wanted to have. So I'll just probably have to do this tomorrow. But essentially, duplicate, and that's going to be B, right? So this is A. And so with B, well, we have this expression, right? And so what we want to do is we want to I'll try to do something in like 2 or 3 minutes. we want to follow these, and again I'll really step back and try to understand why this all makes sense, right? Oh, H bar, awesome. So basically the momentum wave function would be 1 divided square root of 2. You know what, I should actually have these at least like that so I can switch tabs easily. 2 pi is this a thing? It's like H bar a thing in SimPy. Constants H bar, just without the underscore. Times, and then is the integrate, and essentially we're integrating from minus infinite to plus infinite, and we are integrating these times these exponential IPX divided by H bar. IP, well, X, that would be probably R, right? So whatever this is that we're doing these, and then let me see. Preprint, does this compute at least, or no, it's not defined. Why it's not defined? SimPy, there you go. Ah, come on, I don't know if I'm copying these well. I thought that would import it though. Why is I not there? SimPy complex constant I. It's just I. Okay. it's just these. P is not defined. Of course P is not defined. What the fuck is P? Is P just... I think P is just a symbol, but again, I don't know we can assume anything about this. Let me just P. And I'll leave it here, I think, just because I have to go. I want to see if that prints well. Nice. What the... God. Okay. Otherwise, some things are going on here. I just done. Is there a nicer way to 0 or these? I hate these piecewise things. This is just nothing. It is impossible to read. I have to work on that. But okay, I think that is the way you would write that. And so, but what do you do with these? This is then you turn it in. Cool. Yeah, man, it's cool. I mean, I'm archiving all these videos in a YouTube channel called Uncertain Systems. So just, yeah, basically YouTube. There we go. So, and I'm archiving all the sessions in here right away. So you can, you can kind of look at it. They like they have tons of videos, but basically, yeah. And you know that's kind of, again, here is kind of the roadmap for this year. I'm really trying to kind of close that series of quantum mechanics from scratch, basically learning the whole thing just by doing exercises and kind of exploring it live without really following any official material, just kind of using the internet and what's there, Twitter and whatnot. So yeah, man, happy you like it, and feel free to follow. Let's see where that goes, and kind of, you know, I think that's always useful to learn all these skills. Yeah, see you next time. I'll be doing, I try to stream two to three times a week, but then it always depends on the amount of time I have, as this is really purely a hobby, and it depends. Yeah. See you next time.